Hello. For this presentation, I will be talking about modern hydropower. I'm going to talk about some definitions, show you some examples, and discuss the importance and some repercussions of modern hydropower. So really quick, I wanted to go over some definitions. Modern, for this presentation, refers to hydropower in the 21st century. Hydropower has the kind of broad definition of generating energy through the movement of water through the water cycle, which allows us to change the kinetic energy from water to the mechanical energy of water that can be utilized. And then as I go through the different types, I'll further define hydropower and the types. Let's start by going over the basics for how hydropower works. Hydropower uses the water cycle. Water evaporates into the atmosphere. It condenses and falls back down to the earth in the form of precipitation, where it can flow, among other things, through rivers and streams and end up in lakes or oceans. And it eventually ends up back into the atmosphere, completing the cycle. This is a process that most people are familiar with. What's important to note here is that this surface flow into lakes and ocean is what hydropower exploits. It uses the gravitational force of the water. Something that I thought was kind of interesting was that the water cycle is actually driven by the sun. So you could technically say that hydropower is a form of solar energy. But because the energy it captures does come from the hydrologic processes that result from the sun's energy, it is different. But I thought it was something that was interesting to note. I am going to go over the history of hydropower super quick since this presentation is focusing on modern hydropower, but I did want to touch on it. Hydropower has been used throughout history. Water is considered one of the earliest renewable energy sources that's responsible for significantly reducing workload. A water wheel was often used to capture the energy in water. A water wheel uses the flowing river, which is a form of kinetic energy, to turn it and convert the energy into mechanical energy that runs the mill or the grinder that's connected to the wheel. One of the earliest known uses was by ancient Greeks who used the water wheel and the power it generated to grind wheat into flour. Another early civilization that utilized hydropower was the Han Dynasty in China. They used its power to grind grain, break ore, and make paper. So it is likely that the hydropower was utilized even earlier. Both horizontal and vertical water wheels have been noted to be used throughout history, with the vertical wheel being more common and often associated with the early hydropower. The first industrial use of hydropower to generate electricity in the United States occurred in 1880. A majority of the United States hydropower is produced by large dams on major rivers, and many of these dams were actually built in the early 70s. Modern hydropower is almost exclusively used to generate electricity. The common types of hydropower include storage hydropower or impoundment, run-of-river hydropower or diversion, pumped storage hydropower, and offshore hydropower that includes tidal and wave. The next couple of slides will go into detail about these different types of hydropower. The water wheel is also something that is still used today, but not on the same large scale as these other types. Storage hydropower, also called impoundment facilities, are hydroelectric dams. They are the most common type of hydropower today and what most people think of when referring to modern hydropower. They are often large-scale hydroelectric plants, and they generate electricity for things like electric utility projects or the government. They generate electricity by storing river water in a reservoir. The water flows through the penstock that spins the turbine, which generates the electricity, which is then carried to power lines. The importance for a dam is to have an elevation drop so that gravity carries the water through the penstock. The amount of water that is released from the reservoir can change depending on the demand for electricity and maintaining reservoir levels. Dams need to be monitored and maintained throughout the lifetime to prevent dam failure. Maintenance includes clearing the trash rack and inspecting components. If the dam was designed in accordance with good engineering practice and using construction standards, major restoration should not ever be necessary. That being said, there have been some major disasters from dam failure. So a couple examples of dam failures in the past 21st century are the Hope's Mills Dam failure in 2003 in North Carolina. There were no deaths, but 1,600 people were evacuated from the town of Hope Mills, and there was substantial damage. The break caused $2.1 million in damages, to be specific, and the failure was caused by heavy rains. The dam also failed in 2010, and this was due to a sinkhole that formed under the foundation of the dam. It didn't cause quite as much damage as the 2003 failure because the water drained a lot more slowly. In 2006, the Kaloko Dam in Kauai failed during heavy rains and flooding, and this killed 7 people. The failure was believed to have been caused by a multitude of factors, including poor maintenance, lack of inspection, and illegal modifications. Although the United States Army Corps of Engineers designs many dams, there are also privately owned dams that make up a decent portion of dam failures. This graph here shows major dam failures, but it does also include levee failure. For example, the really big dot down in New Orleans, and this was the levee that broke from Hurricane Katrina. A levee, however, is meant to prevent flooding, whereas a dam is designed to generate electricity. So I think that the graph does exaggerate it a little bit. Most states have dam safety programs and laws to prevent dam failure and to ensure public safety precautions such as evacuations are taken during a failure. Run-of-river hydropower, or river diversion. So most of the newer hydropower projects are run-of-the-river. The electricity is generated by diverting up to 25% of the river's flow that flows into a penstock that is either a pipe or a tunnel, which then spins the turbine in the powerhouse. The water is then returned back to the river. The entire river diversion project is made up of a small dam to create the head pond, a pipe or tunnel, a place to house the generators and turbine, often called the powerhouse, and a trail race that returns the water back to the river. Also included are the power lines and access road. Run-of-river hydropower has less of an impact on the environment than other hydropower facilities, as long as they're not clustered or too large. Pumped storage hydropower is the oldest kind of large-scale energy storage. It consists of 2 water reservoirs that are placed at different elevations that generate power as water moves down through pipes and spins a turbine. The water is first pumped up from a lower elevation where it can be stored, and then when energy is needed due to high demand, the water is released and flows down to spin the turbine, generating electricity. There is open loop pumped storage, which refers to projects that are connected to naturally flowing water features, such as a river. And then there's closed loop pump storage that are not connected to a naturally flowing water feature. Although this type of hydropower relies on a net consumer of electricity, they are often still very highly efficient overall. They are often used as a backup to store electricity and used in addition to other energy systems such as, say, wind power. They are considered rechargeable batteries because the water can be pumped back and forth between the two reservoirs. So it's pumped up when the electricity needs are low and then flows back down when the needs become high. Offshore hydropower refers to oceans and accessing the enormous energy reserves that they contain. There are plants that are currently in use in the United States, but this is a power source that's still being established and improved upon. The potential has always been known that the ocean harnesses immense amount of energy, but the technology has been slow to be developed due to many significant barriers. The biggest barriers are the engineering challenges and the associated costs. Some of these challenges include corrosion, cable installation, and software modeling, among others, that really make it difficult to develop these systems that are going to be cost effective. So the offshore hydropower does kind of lump different principles together, such as tidal power and wave power. Waves are an obvious source for offshore hydropower. Tidal power plants use the naturally generated power from waves to generate electricity. This includes tidal turbines and fences, tidal streams, and tidal range. There also exists ocean thermal energy conversion, or OTEC, which is another way that electricity can be generated offshore. And this takes advantage of the temperature gradient between the warm surface and the deeper, colder layers of the ocean. The important thing here is that there needs to be a temperature difference of about 20 degrees Celsius, so it is restricted to certain areas of the ocean. This type of hydropower is still in early development, and it again faces many economic and technological challenges. Hydropower is very important in supporting our energy needs. Hydropower plants produce roughly 7% of total U.S. electricity generation and around 44% of electricity generation from renewable sources in 2017. Hydropower is an important renewable resource. It is a cleaner energy source than fossil fuels since there is no burning fuel and it uses Earth's natural cycle. It is very useful in combination with other renewable energy sources because it can store energy and meet needs during periods of high demand. Hydroelectricity has been proven to be a dependable energy source that, when built properly, requires fairly low operations and maintenance costs. This is also a promising energy source for the future as technology improves and costs decrease. Although hydropower is a clean, renewable energy source, many plants still pose a threat to ecosystems. Hydroelectric plants significantly alter hydrologic systems and wildlife habitat. They affect stream water quality by sediment loading, erosion, pH changes, temperature, and velocity. Dams are quite impactful and can also restrict fish migration and may even build up methane gas in their reservoirs. The building and removal of dams often drastically and suddenly changes an ecosystem. Offshore power also impacts marine animals, causes underwater noise, and disruption of natural movement of the water. The thing to remember with hydropower is the larger the project, the larger the impact there will likely be on the ecosystem and hydrologic system. Projects can be created to avoid some of the environmental impacts, such as turbines that can interact with fish safely, and regular environmental monitoring, and improved technology that can decrease the project size and the way it interacts with natural systems. Overall, this is a much better energy source than fossil fuels when comparing the impact on the environment. Large hydropower plants can also have substantial economic impacts in the way of displacing people from their homes. According to the World Commission on Dams, an estimated 40 to 80 million people have been forced from their lands in the past 6 decades. Often the number of people needing relocation is underestimated during the planning stages. Relocation often results in great cultural and economic harm, and this is an especially significant problem in countries that lack restrictions and laws on the planning, designing, and buildings of dams. Thank you so much for listening. Here is the list of my sources. If you have any questions, leave me a comment below and I will get back to you. Thank you.